Hey chemistry classes, we have done a lot of work over the last few days getting to know our quantum numbers. And so we've learned about the principal quantum number, the angular momentum quantum number, which tells us the shape of the orbital, the magnetic quantum number, which tells us the orientation that the orbital is in, the x, y, or z axis, and then the spin quantum number, which tells us which direction the electron is moving inside of that orbital. Now what we're going to do is we're going to practice something called an electron configuration. And what electron configurations are is they're a visual representation of the way that the atom works. Just a little bit ago, I had drawn a whole atom in its quantum model with all of the different directions that the electron could be moving, and it made this big mess on the board behind me. But now we're going to try a nice and tidy, succinct, organized way to represent the electrons that are present in the atom so that we can understand how the atom will behave. What we'll be learning in our future chapters is that all of the behaviors of an atom, whether it's going to form a cation or an anion, an ionic bond, a covalent bond, whether there are intermolecular forces, they're all kind of based off of this configuration of the electrons. And so this is a way to draw that picture out so that we can see what the atoms look like, kind of what they look like, a representation so that we can understand a little bit more about how they will behave. So let's just look first at what an electron configuration is. The configuration is the way the electrons are arranged in the atom. And there's a special notation that tells us the principal energy level, so whether it's 1, 2, 3, 4, 5, as we move away from the nucleus. The sublevel, is it in the S, the P, or the D orbital? And finally, the direction that that electron is moving. Is it going spin up, remember spin north, or spin south, spin up or spin down? So we're going to be looking at how to represent that for atoms on the periodic table. There are 3 rules that we have to know and keep in mind in order to do our electron configurations correctly. So we're going to look at those rules and then we're going to get started with some practice. The first rule is called Aufbau's principle, and this says that an electron occupies the lowest energy level that can receive it. Imagine you were pouring a glass of water. You would expect the water to come into the glass and go all the way down to the bottom and then fill its way up to the top, right? I would. We would never expect for the water to start at the fill line and then fill its way down. That'd be a really strange glass of water. We do the same thing for our electrons. We expect that whenever we start filling electrons, they're going to start at the closest to the nucleus. If my nucleus is here, according to Aufbau's principle, I would fill each of my orbitals moving up. So we're going to start at the bottom and fill towards the top. So that's what Aufbau's principle will tell us. So we're always going to start at the 1s orbital, or that first orbital that we see in the electron configuration. The second rule is called the Pauli exclusion principle. And the Pauli exclusion principle tells us that an atom cannot have any 2 electrons with the same set of quantum numbers. So you can have 2 atoms that are in the second energy level, the second p energy level, the second p energy level along the x-axis, but if one of them is traveling one direction, the other one needs to be traveling the other direction. And so this is going to give us what we're going to call later the arrow up and arrow down, or spin up, spin down electrons in the atom. The last rule is Hund's rule, and Hund's rule says that electrons want to fill 1 into every orbital at the same energy level before they put in 2. I always think of this as like beds in a hotel, okay? If you were traveling with a sports team and you were going to go stay in a hotel, or you're traveling with your siblings and you were going to go stay in a hotel, if there are 2 queen beds in the room, you guys are going to sleep in each of those beds, right? 1 and 1. But if a third person has to stay in the room, then we double up, right? And if a 4th person, then we double up the other bed. Okay, we don't want to fill up our spaces unless we need to. In Hund's rule, we're going to want to put 1 electron into each space until all of the initial spaces are full, and then we add doubles. These will make more sense as we get started into our orbital diagrams, so let's do it. To get our orbital diagrams ready to go, we're going to start by putting the order of orbitals at the top of the page. So I put the order of the orbitals up here from 1s to 5d, and we're going to be using this as a point of reference as we go through the orbital diagrams. So we're going to start out by doing the orbital diagram for an element lithium. We'll go look on the periodic table and find the atomic number for lithium. Remember, that's the small number that's usually above it. Lithium has 3 protons, and so as a neutral atom, it would have 3 electrons. So I need to make a diagram that shows 3 electrons. The very first orbital that's going to fill for lithium is going to be 1s. So we are going to take these in order, starting at 1s and moving our way up. That is Aufbau's principle. So Aufbau's principle tells us that we always start at 1s. So let's start with 1s. 1s. Now the s orbital has 1 possible orientation. And so for this kind of electron configuration, which we can call an orbital diagram, we're going to put an underline here. This underline represents the 1 orbital of the s quantum number. So this 1 underline is 1 orbital. And how many electrons can 1 orbital have? 2. 1 orbital can have 2 electrons. So we're going to go 1 up and 1 down. 1 spin up and 1 spin down, because the Pauli exclusion principle tells me that I can't put them both as up arrows, because then they would both have the same set of quantum numbers. They would be in 1, they would be in s, they would be in this orientation, this underline, and if they were both up, then that would be all 4 numbers the same. If 1 is up and 1 is down, then that's 3 out of 4 the same. They're close, but they're not the same. The Pauli exclusion principle is telling me that I need to have 1 arrow pointing up and the other arrow pointing down. Remember, the Aufbau principle tells me that I'm always starting at 1s. Okay, now I've put 2 electrons in here, but I need 3. So I'm going to go to my next orbital, which is 2s, 1s, 2s. And I only have 1 electron to put in there, so I'm just going to go ahead and put my 1 orbital in here. Now you might be wondering, could I have drawn my arrow pointing down? Well, sure you could. You could draw your arrow pointing down, but by convention, we draw the arrow pointing up. The first arrow points up, the second arrow points down. That's just how you see it in the books. It's not like, catastrophically wrong. It's just the wrong notation. So it's like a little grammar error, if you want to think of it that way. So this is the orbital diagram for lithium, and I'm going to erase this part and give you guys hopefully a second to make sure you have that written. So our next orbital diagram that I want to do is oxygen. If you look up oxygen on the periodic table, you would find that there are 8 electrons. That's its atomic number. So we're going to start Aufbau's principle, start from the bottom. So we start at 1s. 1s. It gets 1 underline because s always gets 1 underline. I want to remind you guys where I'm getting these numbers from. Remember that we said they count by odd numbers. So this was 1, 3, 5, 7, 9, and 11. And those were orbitals. This should be in your notes. But functionally, this is underlines. And then we said that there were 2 electrons in each orbital. So that makes this 2, 6, 10, 14, 18, and 22. And these were the electrons that could be in there. Functionally, these are going to be the maximum number of arrows. So hopefully that little tip will help make sense of it. But we're going to try a couple more over here. So oxygen, 1s, and we're going to put our 2 arrows in it. You're going to notice I start to get, it's not lazy, it's just a shorthand. I only draw 3/4 of the arrow, so I just draw like part of it. I don't do the other line. You can keep doing the other line if you want to. I just don't by convention. It's been a lot of arrows to draw, so you don't need to do that. The next one is 2s. Because it's s, I do 1 underline and I put my 2 arrows in it. So far that's 4 electrons. I need to keep going till I get to 8 electrons. So what comes after 2s? is 2p. So I'm going to put 2p right here. And p can have 3 underlines, so I'm going to put all 3 underlines here. And now we're going to see Hund's rule for the first time. Hund's rule tells me that I need to put 1 up in every underline before I put any facing down. So this is 4, and I'm going to go 5, 6, 7, and 8. That is 8 electrons. I have drawn 8 arrows, and I have these 2 each in their own space. This is Hund's rule. It tells me that I need to have arrows up before I can fill arrows down. It has to do with the electrons wanting their space and their magnetic fields. Okay, so we're going to want to make sure they have enough space. Okay, let's try another one. You'll notice I'm leaving these things here. I really suggest that for your own papers as well. This is something that you should have not only on your paper, but also when you're going to take the test. This is the information that you need to be effective at filling out orbital diagrams. If you're feeling confused, please stay with me. The more of these you practice, the easier it will become. There's a pattern to this. You just need to give yourself enough time to see it. This time we're going to look at magnesium. Magnesium, Mg, has 12 electrons. Make sure you can find that on the periodic table. The first orbital that fills is going to be 1s. And because it's an s, I'm going to put 1 underline, and then I'm going to put the 2 electrons in that would fill 1s. Next, I'm going to do 2s, and again with my 2 electrons. 2p comes next, and because it's p, remember I'm going to do 3 underlines here. 1, 2, 3, so I have 4 electrons in here so far. I'm going to fill this using Hund's rule, so I'm going to go 4, 5, 6, 7, 8, 9, 10. I'm still not to 12 yet, so I have to keep going. I've done 1s, 2s, 2p. Now I'm going to 3s is next. I have 10 so far. I need to put in 2 more arrows. That's exactly how much space I have. So I'm going to go 1 up, 1 down. There is magnesium. For our next one, we're going to look at aluminum. So if we go look for aluminum, it's in the P block. It's at the top kind of corner of the periodic table, and aluminum has an atomic number of 13. So for aluminum, once again, we start back at the 1s with 1s and 2 electrons in it. And now we have 2s, again with 2 electrons in it. Next comes 2p, and it has 6 electrons in it, followed by 3s, has 2 electrons in it, and finally 3p. 3p has 3 underlines available. But so far I have 2, 4, 6, 8, 10, 12. I only need to put 1 electron in this whole configuration. So I'm just going to put it right here. And everything else stays empty, and that is okay, because that is how aluminum is configured. That's who aluminum is. And it will determine eventually how aluminum behaves. But I can't decide how aluminum behaves unless I see how it truly is. Just like people, right? You gotta see who they are before you can know how they're gonna behave. All right, so good job so far on the orbital diagrams. We're now gonna switch gears, and we're gonna start turning our orbital diagrams into electron configurations. And we're gonna do it using aluminum. So leave aluminum there, and we're gonna switch to its electron configuration. So the orbital diagram is a pretty good shorthand compared to that big atom that we drew earlier. But it still takes up a good amount of room, and it still is a little bit cumbersome to draw. So we're going to do a shorter shorthand that's called the electron configuration. So this is an orbital diagram of the electron configuration. Electron configuration notation consists, we're going to lose the underlines and arrows, and we're going to add an exponent. Okay, so let's look. For aluminum, we're still going to start with 1s. So we're still doing 13 electrons, which now is going to be 13 superscripts, and we'll talk about that in a second. But we still start with one s, but now instead of the underline and arrows, I'm just going to write how many electrons, how many arrows were in that orbital. So in this case, there were 2, right? 1, 2. So 1s, 2. Next, and we just go in a line now, 2s, 2, right there. Okay, so what should come next? 2p, 6. 1, 2, 3, 4, 5, 6. I'm going to count all of them there. And then I'm going to do 3s2, and finally 3p1. And this is what we'll call the electron configuration, and this we'll refer to as the orbital diagram. Good? All right, so let's move on and we'll try some more. Okay, so now we're going to look at calcium, carbon, and sulfur, and we're going to do each of their orbital diagrams and electron configurations. Calcium's atomic number is 20. So we're going to start with 1s, and we're going to do 2 electrons in it. Remember, what am I drawing here? Is this the orbital? What am I drawing here? Is this the orbital diagram or electron configuration? Good, it's the orbital diagram. 1s2, then 2s2, 2p6, 3s2, 3p6. This is a good time to stop and count. So this has 4 electrons. This is 6. That's 10. This is 8 more, so that's 18. I need to make it to 20. So now 4p, what comes after 4p is 4s. And I need 2 more electrons to give me a grand total of 20 electrons. Now if I wanted to do the electron configuration, I would just write it out like this. 1s with 2, 2s with 2, 2p with 6, 3s2, 3p6, 4s2. This will be my electron configuration. Carbon has only 6 electrons, so this one's faster. 1s with 2 arrows, 2s with 2 arrows, 2p. Here's 4, so I just have up and up. 2p2. So let's plug it in. It looks like this. 1s2, 2s2, 2p2. All right, so go ahead and work now on sulfur. Sulfur has 16 electrons. Let's go ahead and do the orbital diagram and electron configuration. This is sulfur's orbital diagram. Now put it into the electron configuration. What should this be? At the very end, 3p, 1, 2, 3, 4. 3p, 4. Very good. So there's sulfur's electron configuration. We're going to do one more together, and for this one, we're going to try to do the electron configuration without doing the orbital diagram first. Save you some time, save you some effort, save you some paper. We're going to try to go straight to those electron configurations. Strontium has a massive number of electrons in it, and using the trick that we learned in class, I think we can tell that strontium is going to end in the S block. And I even think, if we're being very thoughtful about it, that we know that strontium is going to end at 5s. Because if we count down from hydrogen, lithium, sodium, potassium, rubidium, it's in the same line as rubidium. So hydrogen, lithium, sodium, potassium, rubidium, 5, and it's in the S block. So we're expecting to end at 5s. That means that I can move a little bit faster until I get up to the 5s block. So let's try it. So we start with 1s, 2. Remember, we're just taking this line down as we go. That's Aufbau's principle. And we always know how many electrons are going to be in here because we're using this set of numbers right here to tell us. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Let's say you weren't sure if that was the end, if that was as far as we needed to go. Let's stop and do a tally. So we're going to add up all of these little exponents here. So I have 2 plus 2 plus 6. That gives me 10. And I have 2 plus 2 plus 6. That gives me another 10. That means I have found 20 places, but I want to go all the way up to 38, so I need to keep going. 4s2 followed by 3d. Whoa, wow, we haven't seen 3d before. 3d just gets 10 electrons in it. So 3d 10. So now I'm up to, that's another 10. I'm up to 30. I have 8 more to go. I'm going to go, after 3d comes 4p, 6, because p gets 6 electrons. And then finally, I'm going to get to 5s, 2, and these two make 8, and that is 38, and I have done the electron configuration for strontium. It looks harder than it is. It's just a lot of organization. This is a really organized type of thing to do. So if you keep working on your organization, you keep these sets of numbers and these orbitals together, it's a pretty easy way to go. And we're going to be doing more of this in class together the next time I see you.